Physics has a secret it has been keeping for a century. Our most powerful theory of reality contains a glaring contradiction at its very heart. This is the quantum measurement problem. On one hand, the mathematics of quantum mechanics describes a world of smooth, wave-like possibilities, evolving with clockwork certainty. This is the Schrödinger equation, a recipe for a fluid, probabilistic reality. On the other hand, every single experiment we perform yields one sharp, definite result. A click in a detector, a dot on a screen, a live cat or a dead one. Something drastic happens in the instant we look, a jarring transition the theory itself does not explain. This is not a minor technicality. It is a fundamental crack in the foundation of our understanding, challenging everything we think we know about reality, objectivity, and our own role as observers. By the end of this exploration, you will understand why this problem is so serious that it has spawned dozens of conflicting interpretations of reality itself. We will dissect the core paradox, see how it escalates from particles to people, and explore the radical, mind-bending theories physicists have proposed to solve it. How can a theory be spectacularly successful yet fundamentally incomplete? The answer forces us to question the nature of existence. What does it truly mean for something to be real? This duality presents us with a world that behaves in two completely different ways, and the rules for switching between them are nowhere to be found. To see this, we must meet the central character in our quantum drama, the wave function. Think of it not as a physical wave in water, but as a mathematical wave of information, a kind of cosmic probability map. For a single electron, this wave function does not tell us where the electron is. Instead, it describes where it could be, assigning a specific likelihood to every possible location in space. It is a smooth, continuous distribution of potential, and this wave of possibilities evolves over time with perfect, predictable elegance, governed by Erwin Schrödinger's famous equation. It is a clockwork dance of probability. This is the first face of quantum reality, a fluid realm of and. The electron is here and there and over there all at once in a blended state we call superposition. Then we perform an experiment. We place a detector in the path of this electron to finally see where it lands. In that instant, the second face of reality violently emerges. The smooth wave of possibilities vanishes. The detector gives a single, sharp click. A definite particle appears at one specific point. All the other potential locations, all those other possibilities inherent in the wave, simply cease to exist. This abrupt transition from a spread out and to a solitary, or is what physicists call the collapse of the wave function, and here lies the terrifying core of the problem. The beautiful, deterministic Schrödinger equation that describes the wave's smooth evolution says absolutely nothing about collapse. It has no instruction for how or when this sudden jump should happen. The theory provides a perfect recipe for the stew of possibilities, but offers no explanation for why we only ever get to taste one single, definitive spoonful. The boundary between the two faces is fundamentally ambiguous. Is it the physical interaction with the detector? Is it the moment a human being registers the result in their mind? The mathematics is silent. We are left with a theory that tells two contradictory stories, and we have no idea which chapter we are actually living in. Faced with this glaring contradiction, the physics community needed a rule book. The first and most influential attempt came from a group of pioneers in the 1920s, centered around Niels Bohr in Copenhagen. Their solution, known as the Copenhagen Interpretation, was not to solve the paradox but to formalize it. They essentially declared that the wave function is not a description of reality itself, but merely a mathematical tool for calculating probabilities. In this view, it is meaningless to ask what an electron is doing before we measure it. Physical reality with definite properties only crystallizes at the very moment of observation. The act of measurement by a large classical apparatus, like a Geiger counter or a photographic plate, is what forces the wave function to collapse into a single outcome. This interpretation draws a sharp, fundamental line between the quantum world of tiny particles and the classical world of everyday objects. The measuring device must be classical because if it were quantum, it too would enter a superposition and we would never get a definite answer. So the Copenhagen stance makes the collapse itself a basic, unexplained postulate of nature. You simply add it to the rules. For decades, this pragmatic approach was the standard textbook answer. It worked flawlessly for making predictions and building technologies, but philosophically it left a deep unease. It suggests reality is inherently fuzzy until a conscious observer, or at least a machine built by one, looks at it. What then is the universe when no one is looking? The Copenhagen interpretation offers no answer, accepting that some questions are simply beyond the scope of science. For many, this resignation felt less like a solution and more like a surrender. This Copenhagen compromise, however, creates a new and even stranger dilemma. Who or what exactly qualifies as an observer? The problem becomes starkly clear in a famous thought experiment conceived by physicist Eugene Wigner in the 1960s. Imagine a sealed laboratory. Inside, Wigner's friend conducts a simple quantum experiment, say, measuring the spin of an electron. According to the standard Copenhagen rule, the moment the friend reads the result on their detector, the wave function collapses. For the friend inside the lab, the electron now has a definite property. The experiment is over, the result is recorded, and reality is settled. But now consider Wigner himself standing outside the closed laboratory door. From his perspective, the entire lab, including his friend and all the equipment, is just one big, isolated quantum system. He has not yet received any information from inside. According to the very same quantum rules, until Wigner makes an observation of his own, the entire contents of that lab must be described by a single, gargantuan wave function. This wave function would contain a superposition of two possibilities, a reality where his friend saw spin up, and an equally real reality where his friend saw spin down. For Wigner outside, his friend is in a bizarre state of having both seen a result and not having seen it, a blur of contradictory experiences, so we are left with two contradictory accounts of reality. For the friend, collapse happened the instant they looked. For Wigner, collapse only happens when he eventually opens the door and asks for the result. Both are using the same physics, yet they cannot both be correct about when a definite reality came into being. This is not a minor puzzle. It exposes a profound conceptual issue at the heart of the observer-dependent view. If reality only becomes definite upon observation, then whose observation counts, the problem scales infinitely. What if a third physicist is considering Wigner as part of a larger quantum system? This chain of observers leads to a troubling conclusion that facts themselves, the very bedrock of science, may not be objective. They become personal, subjective experiences. The measurement problem thus transforms from a question about particles into a question about consciousness, identity, and the nature of shared reality. It suggests the universe might not have a single, consistent story, but rather a multitude of simultaneous, conflicting narratives, each true for its own observer. This logical chain of observers leads us to a truly bizarre and unsettling conclusion. If the rules of quantum mechanics apply universally, then there is no inherent reason for their strange effects to be confined to the invisible realm of electrons and photons. The mathematics does not contain a size limit. So what happens when we scale these quantum rules up to the world of everyday objects? to things we can see and touch. This is the terrifying genius of Erwin Schrödinger's most famous thought experiment. He imagined a sealed steel chamber. Inside, he placed a living cat. Also in the chamber is a fiendish device, a single radioactive atom connected to a vial of poison. If the atom decays, a hammer shatters the vial and the cat is exposed. According to the quantum rules, that single radioactive atom exists in a superposition. It is both decayed and not decayed. But since the fate of the cat is now tied directly to the state of that atom, the entire system, cat and all, must be described by one giant entangled wave function. This means the cat, locked in the box, is predicted to be in a superposition of two states, alive and dead, simultaneously. It is only when we open the box and look inside that this monstrous wave of possibility collapses into one definite reality, a purring cat or a still one. Of course, we know this is absurd. A cat cannot be both alive and dead. The power of the thought experiment is not to suggest this is physically true, but to shine a glaring spotlight on the central flaw. It asks, where exactly does the chain of superposition stop? If a single atom can be in two states at once, and that state is linked to a hammer, which is linked to a vial, which is linked to a cat, then why does the weirdness not infect the entire system? The seriousness of the measurement problem lies precisely in this scaling up. It forces us to confront the fact that our theory, in its raw form, predicts macroscopic absurdities that we simply never witness. So where is the boundary? Is it at the level of a few atoms, a million atoms, a living creature? The mathematics provides no answer. This is not just a puzzle about cats in boxes. It is a fundamental question about the fabric of reality itself. Why does our world appear so definite, so solid, and so classical, when the underlying rules seem to describe a fluid and ghostly realm of overlapping possibilities? The search for that missing line, the mechanism that prevents our chairs and coffee cups from existing in two places at once, drives the most profound theories in modern physics. The absurdity of Schrödinger's cat forces a critical question. If the mathematics allows for such bizarre superpositions, why does our everyday world feel so stubbornly normal? Why don't we see chairs in two places at once or find our coffee cups both full and empty? For decades, many physicists hoped a process called decoherence might finally provide the answer. It is a beautiful and almost complete solution, one that explains so much about the transition from the quantum to the classical realm. To understand it, we need to abandon the idea of perfectly isolated systems. In the real world, nothing is ever truly alone. A single electron is constantly bumping into stray photons of light, brushing against air molecules, or feeling the subtle tug of distant gravitational fields. Its environment is a chaotic sea of interactions. Now, recall that the hallmark of quantum weirdness, superposition, relies on a delicate phenomenon called interference. This is where the waves of possibility can reinforce or cancel each other out, creating the unique, non-classical patterns we see in experiments. Decoherence argues that when a quantum system interacts with a complex, messy environment, something profound happens. The environment effectively measures the system in a random, uncontrollable way. Each photon that scatters off the electron carries away a tiny piece of information about it. This process is like dropping a single drop of ink into a turbulent river. At first, you can see the ink as a distinct cloud, but within seconds, the countless chaotic currents of the river grab hold of it, spreading and diluting it in every direction until it becomes utterly inseparable from the water itself. The ink's original, coherent structure is lost. In exactly the same way, the quantum system's delicate superposition gets scrambled or entangled with the countless states of the environment. The interference effects that define quantum behavior are washed out, destroyed by this irreversible leakage of information. What we are left with looks, for all practical purposes, like a simple classical probability distribution. The system appears to have randomly chosen one definite state from the menu of possibilities. This is why we never see large objects in superposition. A cat, or even a dust particle, is so overwhelmingly coupled to its environment that decoherence happens faster than we could ever hope to measure. Its quantum weirdness is erased almost instantly, leaving behind the familiar, solid world we experience. So decoherence brilliantly explains the appearance of collapse. It tells us why the quantum realm seems hidden. But here is the crucial, sobering catch that brings us right back to the heart of the problem. Decoherence explains why we see one definite reality, but it does not explain which one. In the mathematics, the process does not eliminate the other possibilities. It simply hides their interference from us. The many possible outcomes, the alive cat and the dead cat, they all still exist in the full description, now just hopelessly entangled with different states of the surrounding environment. From the perspective of the universe as a whole, the superposition persists. Decoherence tells us why an observer like us, who is part of that environment, perceives a classical world. But it does not select a single, objective timeline. The core mystery of the measurement problem, the jump from a fuzzy and to a sharp ore, remains untouched. We have found a powerful reason for the illusion of definiteness, but we are still searching for the mechanism that creates the definite thing itself. Decoherence reveals a universe that remains stubbornly multiple at its core. If the mathematics never truly eliminates possibilities, then perhaps our mistake is insisting that only one outcome can be real. This radical line of thinking leads us to the boldest and most controversial solution of all, the many worlds interpretation. Proposed by Hugh Everett in the 1950s, it makes a stunningly simple claim. The Schrödinger equation is always and universally true. There is no collapse ever. The wave function never breaks. Instead, every single possible outcome contained within it actually happens. When a measurement is made, the universe does not choose, it branches. In our electron experiment, the detector does not click at one random location. It clicks at every location the wave function deemed possible, but each click occurs in a newly created parallel branch of reality. In one world, you see the electron here. In another perfectly real world, an identical version of you sees it there. The cat in the box, it is not in a ghostly mixture. The act of looking causes the single timeline to split. In one branch, you open the box to a living cat. In another, you open it to find the cat has passed. Both outcomes are equally real, but they become forever separate, non-communicating realities. The elegance of this idea is breathtaking. It sweeps away the awkward, unexplained collapse postulate entirely. It restores a pristine, deterministic physics where the wave function just smoothly evolves, no jumps required. The weirdness of superposition is not a problem to be solved. It is simply the description of multiple worlds stacked together. But this pristine solution comes at an immense and serious cost. The first is a staggering ontological price. Reality must continuously and infinitely split at every quantum event, spawning an incomprehensible number of parallel universes every nanosecond. Every possible variation of history, every choice you did not make, every random quantum fluctuation plays out somewhere in this vast, ever-growing multiverse. The second cost is perhaps more troubling for physics. In a branching universe, what do probabilities even mean? If every outcome definitively occurs, why do we observe some as vastly more likely than others? Why do we almost always find the electron where the wave function predicted a high probability, and almost never where it predicted a vanishingly small one? This is the challenge of recovering the Born rule, the mathematical heart of quantum predictions. in a multiverse where everything happens, explaining why we experience this specific, statistically weighted world and not some other becomes a profound puzzle. The many worlds interpretation does not so much solve the measurement problem as it redefines it. The question is no longer why we see one thing, but why we experience this particular thread in an infinite tapestry of realities. The idea of infinite branching universes feels for many like a step too far into the speculative. It asks us to accept a cosmic architecture of unimaginable scale to preserve a single equation. But what if the opposite approach is correct? Instead of accepting the wave function as eternally true, what if we dare to change it? This path leads to a radically different class of solutions known as objective collapse theories. Here, physicists propose that the Schrödinger equation itself is not the final word. It is an approximation, brilliantly accurate for small systems, but missing a crucial term that becomes important for large ones. The most famous of these proposals is the GRW theory, named for its creators Garodi, Rimini, and Weber. Their idea is startlingly direct. They suggest that the wave function of any particle has a tiny, random chance to spontaneously collapse at any moment. For a single electron, this chance is so infinitesimally small that it might only happen once in many millions of years. In this picture, the electron's wave function usually evolves smoothly as Schrödinger predicted. But very, very rarely it will spontaneously snap to a definite location, as if an invisible dice were rolled and came up collapse. This random event is not triggered by any observer. It is a built-in feature of spacetime itself, a new law of nature. Now consider a single electron in your body. Its chance to collapse is negligible. But a cat is made of countless trillions upon trillions of particles. In any given instant, the chance that at least one of those particles undergoes a spontaneous collapse becomes overwhelming. And because all those particles are entangled in the complex structure of the living cat, the collapse of just one can trigger a chain reaction, causing the entire system to snap into a definite state almost instantly. In this view, Schrödinger's cat is never in a superposition of alive and dead, because long before you open the box, the spontaneous collapse mechanism, amplified by the sheer number of particles, has already forced an outcome. The universe itself makes the choice, independent of any conscious observer. The appeal is powerful. It restores a single, objective reality. It explains why we see definite outcomes and why large objects never display quantum weirdness. But this elegance comes with a profound and testable implication. If objective collapse is real, then quantum mechanics as we know it is not fundamentally complete. It is an emergent approximation of a deeper, non-linear theory, and if that is true, then we might be able to detect its signature. Experiments could be designed to look for the subtle deviations this theory predicts. For instance, in a sufficiently large, perfectly isolated mass, we might observe a faint, unexpected heating, a whisper of energy released by these spontaneous collapses. Finding such evidence would be a revolution. It would mean that the fluid quantum realm has a fundamental graininess, a limit to how large and how long a superposition can truly exist. We would have discovered not just how measurement works, but that reality itself has a mechanism for making choices. But what if the very idea of an objective reality is the mistake? All the interpretations we have explored, from Copenhagen's pragmatic fence to many worlds branching cosmos, share one assumption. They treat the wave function as a real thing, a description of the world out there. But a radical school of thought asks us to turn this entire perspective inside out. This is quantum Bayesianism, or QBism. Its solution to the measurement problem is as simple as it is shocking. The wave function is not a picture of reality. It is a personal tool for navigating it. In QBism, the probabilities calculated by the wave function are not statements about what an atom is doing. They are statements about what you, the agent, should believe will happen next. They are personal degrees of belief, like the odds a seasoned gambler assigns to a horse race based on all available information. The gambler's odds are not a property of the horses. They are a property of the gambler's mind, a quantification of their expectations. In exactly the same way, a physicist's wave function for an electron is not a map of an objective electron cloud. It is a coded set of betting odds crafted from past experiments for what that physicist will experience in their next interaction with the lab equipment. This reframing changes everything. The mysterious collapse of the wave function is no longer a physical event. It is a personal update of beliefs. Imagine you have calculated odds for where an electron might hit a screen. You place your detector and it clicks. That click is not the universe violently selecting one reality from many. It is you, the observer, receiving a new piece of data. You now update your internal betting sheet, your personal wave function, to reflect this new certainty. The old probabilities, which represented a spread of possibilities, instantly snap to 100% for the observed outcome and 0 for everything else. The paradox dissolves because there was never an objective superposition to begin with, only a subjective state of uncertain knowledge that became certain. Measurement is just learning. This view elegantly sidesteps the nightmares of Wigner's friend and Schrödinger's cat. Your friend in the lab has their own wave function, their own personal betting odds. When they see a result, they update their beliefs. You, outside the door, have your own separate set of odds, which you will update when you hear their report. There is no contradiction because there is no single, God's eye view of reality to contradict. Facts are not universal in QBism. They are intensely local and personal. The cost of this elegant solution, however, could not be higher. QBism asks us to abandon the dream of a single, shared physical reality described by physics. The universe it gives us is not a grand clockwork or a branching tree, but a collection of individual perspectives, each with its own internally consistent but fundamentally separate story. The rock-solid world you see and touch is, in this view, not an objective stage. It is the stable, shared pattern that emerges from countless personal experiences and interactions. For some, this feels like a profound liberation, finally placing human experience back at the center of science. For others, it feels like a retreat into solipsism, a surrender of science's core mission to describe a world that exists independently of us. QBism does not tell us what the world is. It tells us how to live successfully within the one we experience. Faced with such dizzying philosophical choices, a large portion of the physics community has adopted a very different posture. They choose to sidestep the interpretive maze entirely through a pragmatic philosophy known as instrumentalism. Its unofficial motto is a blunt three-word directive: shut up and calculate. This stance argues that the true purpose of quantum mechanics is not to tell us what reality is, but to provide an exquisitely precise mathematical instrument for predicting the outcomes of experiments. The wave function, under this view, is not a map of an objective world. It is a tool in a toolbox, a set of rules for manipulating symbols that yield astonishingly accurate numbers. Asking what the wave function really represents, or what happens during measurement, is seen as a meaningless diversion, a philosophical quagmire that distracts from the real work of doing physics. For an instrumentalist, the theory is a black box. You feed in your initial setup, you turn the mathematical crank, and out pops a probability distribution that tells you what your detectors will likely show. What happens inside the box, the nature of reality itself, is irrelevant. This approach is undeniably powerful and productive. It is the engine behind our most advanced technologies, from the lasers in your DVD player to the design of quantum computer chips. Engineers and applied physicists can build revolutionary devices without ever taking a stance on many worlds or objective collapse. They simply use the equations that work. Yet this very success highlights the profound seriousness of the measurement problem. The instrumentalist retreat is not a solution, it is a symptom. Historically, physics has aimed for more than just prediction. Its great ambition has been to describe the world as it truly is, to uncover the mechanisms behind the phenomena. Newton did not just give us equations to calculate planetary motions. He gave us a conceptual framework of forces and universal gravitation that painted a picture of cosmic order. To abandon that descriptive quest, to declare that our most fundamental theory is merely a calculational recipe with no corresponding story about reality, represents a significant philosophical surrender. It admits that at the deepest level we currently probe, our mathematics and our intuition have become utterly disconnected. We are left with a supremely useful tool whose operating manual is written in a language we do not fully understand, for a reality we dare not describe. Choosing to just calculate is, in its own way, a stark admission of the problem's depth. It is the acknowledgement that the mystery is so profound, so resistant to our classical intuitions, that for many the only rational response is to stop asking the question altogether and focus on what the equations can reliably build. The instrumentalist might choose to ignore the question, but the equations themselves hold a deeper mystery. Even if you accept that the wave function collapses or that the universe branches, a fundamental puzzle remains. Where do the numbers come from? In every quantum experiment, the theory doesn't just say an electron could be here or there. It assigns precise odds. It tells us a specific outcome is, say, 80% likely, while another is only 20% likely. These are not just guesses. They are calculated directly from the wave function's amplitude, following a precise mathematical recipe called the Born-rule. You take the amplitude, a complex number from the wave, and square its magnitude. That squaring operation gives you the probability. This rule is the absolute bedrock of quantum prediction. It works flawlessly, but why does it work? Why should squaring the amplitude give us the correct odds? This is not a trivial question. It is a gaping hole in the logical structure of the theory. The other postulates, like the Schrödinger equation, describe how the wave evolves. The Born-rule is then simply tacked on as an extra, separate commandment. It tells you how to translate that evolving wave into a set of numbers you can actually test. No one has successfully derived the probabilistic Born-rule from the deterministic wave equation alone. They are separate pieces of the puzzle, and the connection between them is assumed, not proven. This becomes a monumental challenge for interpretations like many worlds. In a universe that deterministically branches into every possible outcome, what does probability even mean? If both the live cat branch and the dead cat branch are equally real, why do we expect to find ourselves in one branch 80% of the time and the other branch only 20% of the time, based on the squared amplitude? From the perspective of the multiverse, every branch is 100% real for the version of you in it. So how do we recover our overwhelming experience of statistical weighting, of some events feeling common and others feeling extraordinarily rare? Some proponents suggest that probabilities correspond to the measure of branches, that there are somehow more branches for high probability outcomes. But this is tricky because the mathematics describes a continuous splitting, not a countable set of discrete paths. Others argue that probability is about the self-locating uncertainty of a conscious observer finding themselves in one branch versus another after the split. Yet deriving the exact squared rule from this idea of ignorance has proven fiercely difficult. The problem of the Born-rule forces a humbling realization. Our most successful theory is built on a probabilistic engine whose own source of randomness we cannot fully explain from within the framework. We have the answer, but we are still searching for the reason why it is the answer. The mystery of measurement becomes even more profound when we realize it is not a local affair. It is not confined to a single point in space. This brings us to one of the most shocking discoveries in 20th century physics. a revelation that ties the fate of distant particles together in a way Einstein himself called spooky action at a distance. To understand this, we must revisit a famous challenge from 1935, known as the EPR paradox, named for Einstein, Podolsky, and Rosen. Their argument was a masterpiece of logical deduction aimed at proving quantum mechanics was incomplete. They imagined a pair of particles, like two electrons, created together so that their properties are perfectly correlated or entangled. These particles then fly apart to opposite sides of the galaxy. According to quantum mechanics, until you measure one, neither particle has a definite spin, say, up or down. They exist in a shared cloud of possibility. Now, Einstein argued this is absurd. If you measure the left particle and find its spin is up, you instantly know with 100% certainty that the right particle, now light years away, must have spin down. For Einstein, this meant the right particle must have had that definite property all along. The measurement on the left simply revealed a pre-existing fact, like finding one glove in a pair is left-handed and instantly knowing the other is right-handed. He concluded that quantum mechanics must be incomplete because it failed to describe these hidden, definite properties. There must be a deeper, local reality where objects have actual states independent of measurement, and no influence can travel faster than light. For decades, this seemed a compelling philosophical argument. Then, in the 1960s, physicist John Bell found a way to test it. Bell's theorem is not a theory, but a mathematical proof. It showed that if Einstein was correct, if there are local hidden variables determining outcomes, then the correlations between entangled particles would have to obey certain strict limits. Quantum mechanics, however, predicts correlations that smash right through those limits. The universe had to choose. Either particles have local, predetermined properties, or quantum mechanics is correct and something truly non-local is happening. Starting in the 1970s, a series of increasingly precise experiments, led by pioneers like Elaine Aspect, put the question to nature. The results were unequivocal. The quantum predictions were confirmed. The Bell inequalities were violated. This means Einstein's comforting view of a local reality is impossible. There are no hidden instructions carried by each particle. When you measure one entangled particle, its distant partner does not just have its property revealed. Its state is genuinely determined by that far-away measurement. The correlation is instantaneous regardless of distance. This is non-locality. It tells us that the fabric of reality is woven with connections that operate outside our normal understanding of space and time. And this brings us back to the measurement problem with terrifying force. That moment of collapse when a possibility becomes a fact is not just a local event. It is a global update. It seems to resonate across the universe, instantly selecting a definite state for a particle that may be on the other side of the cosmos. The problem is no longer just about when or why a wave function collapses. It is about how that collapse communicates itself faster than light, stitching a single, definite reality into place everywhere at once. The act of looking here, it seems, can rewrite the state of reality over there. This entanglement of everything forces us to reconsider the most basic currency of reality. What if the universe is not made of tiny, solid particles, but of something far more abstract? What if it is made of information? This perspective, born from wrestling with the measurement problem, suggests that physics is not about what is, but about what is known. The pioneering physicist John Wheeler captured this radical shift in a simple, cryptic phrase, it from bit. He proposed that every particle, every field, even spacetime itself, ultimately derives its existence from binary answers to yes or no questions, from bits of information. In this view, a particle's position is not a primary fact of the world. It is the answer to a query posed by an interaction. The universe is not a grand machine of moving parts, but a vast, self-organizing network of relationships and measurements. The act of observation is not an annoying interruption to reality. It is the very process that brings reality into sharp focus. But this raises the same old question in a new form. If reality is a tapestry woven from information, why does it appear so consistent to all of us? Why do you and I agree on the location of a chair, if that location is just an answer to a question? This is where a powerful modern idea called quantum Darwinism enters the stage. It attempts to explain how objective, classical facts emerge from the quantum fog through a kind of natural selection of information. Recall the process of decoherence, where a quantum system's fragile superposition gets scrambled by its environment. Quantum Darwinism looks at this not as a loss, but as a proliferation. When a system interacts with its surroundings, certain information about it, like its position or its momentum, gets copied over and over again. A photon bounces off an object and carries a snapshot of its location to your eye. A trillion air molecules scatter off it, each one encoding a tiny piece of the same data. This information is broadcast, replicated, and disseminated into the environment. The key insight is that not all quantum information is copied equally. The highly specific, fragile details of a full superposition are lost to the noise. But a few robust, stable features, the very ones we recognize as classical properties, are redundantly imprinted onto countless fragments of the environment. These are the surviving pieces of data. In this framework, you do not directly see a cup on a table. What you see, what any observer sees, is the multitude of redundant records of that cup's position that have spread through the light and the air. Objective reality, the world we all agree on, is not a single, privileged state. It is the consensus formed from the most widely available, most frequently copied information. The cup is classical because its location has been published in a near infinite number of environmental newspapers. Its more subtle quantum secrets remain locked in a private, unreadable diary. This is the quasi-evolutionary process. The environment acts as a selective amplifier, favoring the spread of certain stable information, while other possibilities simply fade from view, lacking any robust copies. It explains why we all share the same macroscopic world, without needing a magical collapse or an infinity of branching worlds. We are all just observers tapping into the same, widely broadcast data stream. Yet, even this elegant framework leaves a haunting echo of the original problem. Quantum Darwinism explains why we perceive a stable reality, but the initial choice of which information gets redundantly copied is still dictated by the quantum laws we started with. It describes the mechanism of consensus, but the underlying mystery of the quantum probability rule, the source of the original data being broadcast, remains. We have found a plausible story for how reality becomes objective, but we are still deciphering the first line of the manuscript from which it is read. Theoretical debates can only take us so far. To truly understand the measurement problem, we must ask the universe itself. This has led to a breathtaking new frontier in experimental physics, one that directly challenges the boundary between the quantum and classical worlds. Scientists are no longer content to theorize about Schrödinger's cat. They are actively trying to create its microscopic cousins in the laboratory. The quest is to coax larger and larger objects into the delicate state of quantum superposition, to see just how far quantum weirdness can stretch before it snaps. The first steps were with atoms, then molecules. In landmark experiments, researchers have successfully placed molecules composed of hundreds of atoms into a superposition, interfering with themselves as they pass through a device like a wave. These are not just theoretical points, they are complex structures with thousands of protons and neutrons behaving in ways that defy our everyday intuition. But the ambition grows. The next targets are nanomechanical oscillators, tiny but visible silicon paddles or membranes, smaller than a grain of pollen but still containing trillions of atoms. The goal is to cool such a device to near absolute zero, isolating it from its environment with exquisite care, and then put its entire physical motion into a superposition. Imagine a single, tiny vibrating drumhead being in two different vibrational states at once, a literal object existing in two places simultaneously. These experiments are not just for show. They are critical tests for objective collapse theories like the GRW model we discussed. There is a predicted limit. As an object's mass increases, the rate of spontaneous collapse should increase. If we can create a superposition in an object massive enough, we might finally witness the collapse mechanism in action, seeing the superposition disappear on a schedule the standard quantum theory does not predict. It would be direct evidence that the Schrödinger equation is not the final word. Conversely, if we can push the mass and size further and further without seeing any breakdown, it strengthens the case for interpretations like many worlds, where size is no barrier to superposition, only environmental isolation is. This experimental arms race even extends to speculative proposals involving biological entities like specially prepared viruses. A virus exists in a strange borderland between chemistry and life. Could such a structure, with its intricate, folded proteins, be placed in a superposition of two quantum states? The technical challenges are monumental, but the question is profound. Would a living organism, even a simple one, interact with the quantum realm in a fundamentally different way than a crystal or a silicon chip? Each successful experiment, each leap in mass and complexity, chips away at the presumed wall between the two realms. We are actively mapping the shoreline where the quantum ocean meets the classical land, searching for its cliffs or its gentle sands. Every time we push the boundary and find that quantum rules still hold, it forces us to reconsider what our macroscopic world is really made of. If a molecule can be in two places, why not a dust speck? If a dust speck, why not something larger? The experiments are asking nature to reveal its rulebook, page by painstaking page, in the hope of finding the missing chapter on measurement itself. These experiments push against the very limits of reality as we know it, but there may be an even deeper layer to this mystery. To find it, we must look beyond quantum mechanics and toward its greatest unfinished union, the attempt to marry it with Einstein's theory of gravity. This quest reveals a startling possibility. The measurement problem and the very nature of time itself might be two sides of the same coin. In our everyday world, time flows forward, an irreversible river carrying us from a definite past into an uncertain future. This feels fundamental, yet in the pristine equations of general relativity, time is not a flowing river. It is more like another dimension of space, woven into a static, four-dimensional block of spacetime. All of history, past, present, and future, just exists. This block universe view is strange enough, but when physicists try to quantize gravity, to describe the fabric of spacetime with quantum rules, something even more bizarre happens. The most straightforward approach, called canonical quantum gravity, leads to the Wheeler-DeWitt equation. This is a quantum description of the entire cosmos. And in this equation, something profound is missing. The time variable simply cancels out. The equation describes a universe that is, in a deep mathematical sense, frozen and timeless. It presents reality as a single, unchanging quantum state that contains all possible configurations of matter and geometry at once. There is no now ticking forward, no obvious arrow from past to future. This is the famous problem of time in quantum gravity. Our overwhelming experience of temporal flow seems to vanish from the fundamental description. Now hold that thought and return to our core dilemma. The measurement problem is about how indefinite possibilities become a single, definite now. When you measure an electron, you get one result, and that result becomes a settled fact of history. the fuzzy quantum present crystallizes into a sharp classical past. This act creates a before and an after, a division in the timeline. What if these two puzzles are intimately linked? The timeless universe of the Wheeler-DeWitt equation is like a cosmic version of the unmeasured quantum state. It is a superposition of every possible history, every arrangement of particles and galaxies, all existing at once in a grand, static blend. In such a picture, there is no flow because there is no single thread to follow. The emergence of time as we feel it, the sensation of a moving present, might be directly tied to the process that selects one definite history from that vast menu of possibilities. In other words, the act of measurement which creates definite facts could also be what creates the illusion of time's flow. Each measurement, each quantum event that becomes definite, adds one more fixed point to the block of spacetime. From our perspective inside the universe, trapped within this process, it feels like time is passing. We are not moving through time. We are, in a sense, building it as we go, with each observation laying down another stone in the path of a single, consistent history. This is a speculative but breathtaking connection. It suggests that the reason we cannot find a neat, clean solution to the measurement problem within standard quantum mechanics is because the problem is not purely quantum. It is a symptom of a deeper cosmological issue, a clue about how a timeless, quantum description of everything gives rise to our lived experience of a sequential, classical world. The mystery of why we see one reality and not another might be inseparable from the mystery of why we experience a now at all. Both point toward a profound truth that our classical reality of objects, events, and time itself is not the foundation of the universe, but a remarkable and persistent illusion that emerges from a more fundamental and far stranger quantum whole. This connection between time and observation leads us to a final, deeply controversial hypothesis. What if the observer is not just a passive recorder, but the very catalyst of reality? This idea suggests consciousness itself causes the wave function to collapse, proposed in various forms by thinkers like Eugene Wigner and John von Neumann. This view takes the observer dependence of the Copenhagen Interpretation to its ultimate conclusion. It argues that physical devices like Geiger counters or cameras are not enough. They are simply complex quantum systems themselves, which would also enter superpositions. Only when the information from that device reaches a conscious mind, a living, thinking observer, does the chain of possibilities finally resolve into one definite fact. In this picture, the universe exists in a shimmering haze of potential until a moment of awareness crystallizes a piece of it into solid experience. The tree falling in the forest truly makes no sound if no one is there to hear it, because without a conscious observer, the event remains an unmade choice in the quantum fog. The appeal of this idea is its stark, almost poetic simplicity. It places human experience, or perhaps any conscious experience, at the very center of the cosmic story, not as an accident but as a fundamental creative force. It seems to answer the who in Wigner's friend paradox definitively. The friend's consciousness is the final trigger. Yet for all its philosophical intrigue, this hypothesis faces overwhelming scientific objections. First and foremost, it is profoundly untestable. We have no scientific definition or measure for consciousness, no meter to detect its presence or quantify its intensity. We cannot design an experiment to see if a superposition collapses for a cat, a computer, or a comatose patient, because we have no independent way to verify the internal state of awareness. This makes the proposal more of a metaphysical statement than a physical theory. Secondly, it introduces a strong form of dualism into physics, the idea that mind and matter are separate substances. It suggests the laws of physics which govern atoms and energy are incomplete until they interact with something entirely non-physical, consciousness. This creates an explanatory gap wider than the one it tries to close. We would be replacing the mystery of collapse with the even deeper mystery of how an immaterial mind influences physical atoms. Finally, it commits a serious logical misstep. It attempts to explain one profound unknown, the measurement problem, by invoking another profound unknown, the nature of consciousness. This is not an explanation, it is a relocation of the puzzle. Placing an unexplained primitive at the heart of physics does not simplify our model of the world. It complicates it beyond any hope of a unified framework. While the question of consciousness and its relation to reality remains one of our greatest puzzles, most physicists see this particular proposal as a dead end, a fascinating but ultimately unscientific detour in our quest to understand the quantum world. But what if the very concept of an absolute fact is the error we have been making all along? A powerful and elegant interpretation, known as relational quantum mechanics, proposes exactly this radical shift. Developed by physicist Carlo Rovelli, it takes a step back from the dizzying choices between many worlds or a single collapse. Instead, it suggests we have been asking the wrong kind of question. We have been searching for a God's-eye view of the universe, a single, true description of what the electron or the cat really is. Relational quantum mechanics argues that no such perspective exists. In this view, quantum states are not absolute properties of objects. They are always and only defined relative to another physical system. An electron does not have a spin-up or spin-down in itself. It has spin-up relative to the detector that just measured it, and it could, without contradiction, have spin-down relative to a different detector that interacted with it in another way. The information is not a picture of reality, it is a record of a specific relationship. Apply this to our troubled cat in the box. In the relational picture, it is meaningless to ask if the cat is absolutely alive or dead. We can only ask about its state relative to something else, relative to the vial of poison and the decaying atom inside the box. The cat's fate may be settled. That small internal environment has interacted and established a fact, but relative to you standing outside the sealed laboratory, the cat's state is still indefinite, a superposition of possibilities, because you have not yet interacted with the system to establish a relationship. Both descriptions are equally valid and true, but they are true for different observers. There is no single, overarching reality that contains a contradiction, because facts themselves are not universal. They are local and relational. This reframes the entire measurement problem. The jarring transition from possibility to fact is not a physical collapse that happens once for everyone. It is simply the updating of information within a specific relationship. When you finally open the box, you enter into a new physical interaction with the contents. At that moment, you establish a relationship, and relative to you, the cat's state becomes definite. The universe does not choose one history. It simply weaves a consistent web of correlations between all the interactions that occur. This is a profoundly democratic view of reality. It gives equal weight to every perspective, from a single photon scattering off an atom to a human scientist reading a dial. But this elegant solution carries a profound and perhaps unsettling cost. It means a complete God's-eye description of the universe is fundamentally impossible. Physics cannot give us the view from nowhere because there is no such place to look from. Every description, every fact, every bit of reality is tethered to a particular point of view within the system. We are not outside observers of a clockwork universe. We are participants in a vast, interconnected network, and the story we tell is always the story of our particular connections. All these interpretations may seem like abstract philosophy, but their resolution carries immense weight far beyond the lecture hall. It sits at the very heart of the most promising technological revolution of our time. Quantum computing, quantum cryptography, and quantum sensing are not science fiction. They are being built in laboratories right now, and their entire promise hinges on our ability to manipulate and sustain the very phenomenon at the center of the measurement problem, superposition. The most formidable enemy of these technologies is decoherence, the process where a delicate quantum state loses its coherence and collapses into an ordinary, classical bit of information. This is not a theoretical nuisance. It is the primary engineering hurdle, the relentless countdown timer that limits every quantum calculation. In a quantum computer, information is stored in quantum bits or qubits. Unlike a classical bit that is definitively a 0 or a 1, a qubit exists in a superposition of both states. This allows it to perform calculations along many pathways simultaneously, a parallelism that promises to solve certain problems exponentially faster than any conventional supercomputer. But maintaining that superposition is a constant battle against the environment. A stray photon, a vibration in the lattice, even the faint magnetic whisper of the Earth can act as an unintentional measurement, causing the qubit to decohere and the calculation to fail. Current quantum computers are essentially gigantic, ultra-cold isolation chambers, fighting to protect their fragile quantum states from the classical world's constant intrusion. This is where the fundamental physics directly meets practical engineering. If we understood the quantum to classical transition more deeply, if we could pinpoint exactly how and why decoherence happens in specific materials and architectures, we could design better shields. More importantly, we could develop far more sophisticated quantum error correction codes. These codes are like protective spells, using extra qubits to monitor and correct the errors that decoherence introduces, without directly measuring and collapsing the main qubits themselves. But to design the most efficient codes, we need the clearest possible model of the enemy. Is decoherence simply information leaking into the environment, as the standard theory suggests? Or could there be a hint of something else, like a spontaneous collapse mechanism that becomes significant at certain scales? The answer dictates our strategy. The same urgency applies to quantum cryptography, which uses the principles of quantum entanglement to create theoretically unbreakable codes. The security guarantee relies on a fundamental fact. Any attempt to eavesdrop on an entangled photon pair constitutes a measurement, disturbing the system in a detectable way. But this guarantee assumes we perfectly understand what constitutes a measurement. If our model is incomplete, could there be a subtle, undetectable way to glean information? Pushing the boundaries of these technologies is, in essence, a massive, ongoing experiment in foundational physics. Every time engineers extend the coherence time of a qubit, they are empirically testing the limits of quantum superposition. Every successful quantum encryption over a longer distance provides evidence about how entanglement survives in the real world. The measurement problem has thus transformed from a century-old philosophical debate into a multi-billion-dollar engineering challenge. Solving it, or at least understanding it better, is not just about satisfying our curiosity about reality. It is the key to unlocking computational powers that could reshape medicine, materials science, and our understanding of complex systems. The race to build a practical quantum computer is, in a very real sense, a race to finally master the mysterious moment when possibility becomes fact. For decades, this profound puzzle was politely pushed to the sidelines of mainstream physics. The measurement problem became the eccentric uncle at the family reunion, acknowledged with a nod but rarely engaged in serious conversation. Why would a field dedicated to probing the deepest truths of nature sidestep its most glaring conceptual challenge? The answer lies in a powerful historical and cultural context that shaped 20th century science. In the years following quantum mechanics' explosive birth, a pragmatic consensus solidified around the Copenhagen Interpretation. It was less a complete philosophy and more a working truce, a set of rules that produced stunningly accurate results. This Copenhagen dogma became the standard curriculum, taught not as one interpretation among many, but as the correct way to understand the quantum world. Questioning its foundations was often seen as a sign of not truly understanding it, a kind of philosophical indulgence. The sheer, intoxicating success of the theory fueled this attitude. Quantum mechanics became the engine of a breathtaking century of discovery. It predicted new particles, explained the stability of atoms, and laid the groundwork for lasers, transistors, and semiconductors. Physics was on a roll, unlocking the secrets of the nucleus and the cosmos. In this gold rush of predictive power, stopping to fret over what the equations meant seemed like a pointless distraction. Why fixate on the blueprint of the machine when it was producing such miraculous gadgets? The focus shifted overwhelmingly to application and calculation. This was the rise of instrumentalism, the shut up and calculate mentality, from a practical tool into a dominant cultural stance. Careers were built, Nobel Prizes were won, and technologies were invented by those who skillfully manipulated the mathematical machinery without ever asking what turned the gears. To spend one's time on foundational questions was, in many prestigious circles, considered a career risk, a departure from real physics into the murky waters of metaphysics. The problem wasn't solved, it was simply declared out of bounds. This historical neglect created a curious gap. We developed a theory that works with unparalleled precision, yet we conditioned generations of physicists to avoid discussing what it tells us about the nature of reality. The current resurgence of interest in quantum foundations is, in many ways, a correction to this long neglect. It is the recognition that a science which refuses to confront its own deepest paradoxes is incomplete. The gadgets work, but the mystery remains, and we are finally turning back to face it with fresh eyes and new tools. So we stand at a crossroads of realities, each path paved by a different interpretation. Each promises to resolve the measurement problem, but every one demands a profound concession, a trade-off that reshapes our entire picture of the universe. The Copenhagen Interpretation offers pragmatic clarity. It gains a clean, operational rulebook for doing physics, a clear line between the quantum and classical worlds we can use to build technology. Its price, however, is a deep philosophical resignation. It surrenders the dream of a reality independent of measurement, accepting a universe that is fundamentally fuzzy until observed. It introduces the observer as a mysterious, unexplained agent at the heart of physics, and it leaves Wigner's friend in a paradoxical limbo. You gain a tool, but you lose a world that exists on its own. The many worlds interpretation purchases elegant purity. It gains a breathtakingly simple and complete physics, where the beautiful Schrödinger equation is the only law, governing a reality without random jumps or collapses. The cost is an ontological explosion of staggering proportions. It asks us to believe in an ever-branching multiverse of infinite, equally real copies, where every possible quantum outcome physically exists. The problem of probability becomes acute, and we must explain why we experience this specific thread in the infinite tapestry. You gain a single, deterministic law, but you lose a single, shared universe. Objective collapse theories restore a single, objective timeline. They gain a real world where facts are universal and measurement is a physical process like any other, triggered by a new law of nature. The serious price is a departure from standard quantum mechanics itself. It requires adding a new, non-linear term to the most successful equations we have ever written, a fundamental modification of physics that must be hunted down in delicate experiments. You gain one real world, but you lose the pristine, unmodified quantum theory. Finally, QBism reframes the entire game. It gains a stunningly elegant dissolution of the paradox, turning the wave function into a personal guidebook and measurement into a simple update of belief. It neatly avoids the paradoxes of Wigner and Schrödinger by making every fact observer relative. The monumental cost is the very idea of an objective, shared physical reality. The universe becomes a collection of individual perspectives, and science shifts from describing the world as it is to charting a stable consensus of experiences. You gain internal consistency and peace of mind, but you lose the objective stage upon which the drama of physics was supposed to unfold. This is the stark landscape of our dilemma. There is no free lunch in the search for quantum reality. Every potential exit from the maze requires a leap of faith, a willingness to accept a profound and strange new vision of existence. The measurement problem is so serious precisely because its solutions force us to choose which foundational pillar of our understanding we are most willing to relinquish. Do we give up an objective world, a single universe, a pristine theory, or a mind-independent reality? The choice is not merely technical, it is deeply personal, a question of what we believe physics is ultimately meant to describe. This unresolved tension between the quantum and the classical may be pointing toward an even deeper fracture in our understanding of the cosmos. The measurement problem is not an isolated philosophical curiosity. It is a symptom of a much grander schism, a fundamental conflict between our two most successful theories of reality, quantum mechanics and Einstein's theory of gravity, general relativity. Each theory reigns supreme in its own domain, yet they are built on foundations that appear utterly incompatible. Unifying them into a single theory of quantum gravity is the holy grail of modern physics, and at the heart of this quest lies our very same dilemma, the nature of definiteness. Quantum mechanics, as we have seen, is built on a bedrock of potentiality. Particles exist in superpositions, locations are smeared clouds of probability, and reality remains fluid until an interaction occurs. Its canvas is the fuzzy, probabilistic world of the very small. General relativity, in stark contrast, paints on a canvas of absolute certainty. It describes the cosmos at its grandest scales, where matter and energy warp the fabric of spacetime itself into a definite, smooth, and continuous geometry. Planets follow curved paths not because of a mysterious force, but because they are tracing the immutable contours of this geometric landscape. In Einstein's universe, spacetime is not a suggestion. It is a precise, deterministic structure. Herein lies the core conflict. Quantum theory demands that everything, including the gravitational field, should be subject to superposition and uncertainty. This implies that spacetime itself, the very stage upon which reality plays out, should be able to exist in a blurry, indefinite state. We should be able to have a superposition of different curvatures, a reality where space is both warped one way and another simultaneously. Yet general relativity insists that spacetime geometry is singular and definite. It cannot be a probability cloud. It must be a specific shape for the theory's equations to even make sense. The clash is not merely a technical disagreement about how to quantize a force. It is a war over the most basic nature of reality. Is the universe fundamentally fuzzy and probabilistic, or is it a precisely geometric, deterministic block? The measurement problem sits at the explosive intersection of this war. In our current, separate theories, we simply postulate that measurement magically resolves quantum fuzziness into classical definiteness. But in a unified theory of quantum gravity, there can be no such outside intervention. There is no larger, classical spacetime to host the measurement apparatus, because spacetime itself is part of the quantum system being described. The universe has to account for its own definiteness from within. This forces a breathtaking possibility. A successful theory of quantum gravity may not be able to avoid the measurement problem. It may be compelled to solve it. The mechanism that selects one definite spacetime geometry from a quantum superposition of many could be the very same mechanism that explains why any measurement yields a single result. Perhaps the emergence of a classical, smooth spacetime from a frothing quantum foam is not a separate process from the collapse of a wave function. They could be one and the same event, viewed at different scales. Conversely, it is equally plausible that we cannot build a coherent theory of quantum gravity until we first understand what makes quantum possibilities crystallize into classical facts. Our attempts to quantize spacetime keep hitting mathematical infinities and paradoxes. Could it be that these are not just calculational hurdles, but signs that we are missing the correct description of how quantum indefiniteness transitions to the definite world we experience? Solving the measurement problem might provide the crucial conceptual key, the missing principle that tells us how and why a single, consistent history of spacetime emerges from the quantum fog. The quest to unite the very large with the very small is therefore more than a merger of equations. It is a search for the narrative that bridges possibility and actuality, a story that explains not just how gravity works on a quantum scale, but how anything at all becomes real. This final confrontation reveals the true stakes of our century-long investigation. The measurement problem is far more than a technical glitch in our equations. It is a profound philosophical challenge, one that forces us to question the very meaning of reality itself. At its core, the puzzle asks us to define what we even mean by a measurement. Is it any physical interaction? Is it the registration of information in a complex system? Or does it require a moment of conscious awareness? We have no agreed-upon answer, and this ambiguity ripples outward, unsettling everything we thought we knew. If we cannot cleanly define the act that creates facts, then what exactly are facts? This pushes us into the domain of ontology, the philosophical study of what truly exists. Science has always operated on the assumption of a real, objective world out there, waiting to be discovered. But quantum mechanics in its raw form seems to undermine that very assumption. It presents a reality that is fluid, potential, and observer-dependent. So we are left with a haunting question. Does the universe exist in a definite state when no one is looking? Or is our observation somehow integral to its very existence? This is not mystical speculation. It is a direct consequence of the mathematical formalism we use to make the most accurate predictions in human history. The seriousness of the measurement problem lies precisely in this escalation. It begins as a puzzle about electrons and detectors, but it inevitably expands into a crisis of meaning for physics as a whole. Are we describing a world that exists independently? Or are we describing the structured patterns of our experience within that world? Every interpretation we have explored is at heart a different answer to this ontological question. The Copenhagen view essentially says that reality is not fully formed until measured. The many worlds view says everything that can happen does happen in a vast multiverse, making reality far larger than we perceive. Objective collapse theories say reality is singular but governed by a new, spontaneous law. And QBism says reality is personal, a web of individual perspectives. Each offers a different vision of what is fundamentally real. This is why the problem endures. It is not a gap in our knowledge waiting for one more experiment to fill it. It is a fork in the road of understanding where we must choose which foundational principle we value most. A single universe, a pristine theory, an objective world, or a coherent personal experience. The measurement problem compels us to decide what story we want science to tell, not just about particles, but about the nature of existence. And until we find a way to test these grand visions with definitive experiments, the question of what makes something real will remain the most serious and most human problem in all of physics. A century of investigation has left us not with an answer, but with a deeper appreciation for the question. The profound seriousness of the quantum measurement problem lies precisely here. It is not a minor bug at the edge of our most successful theory. It is a fundamental inconsistency at its very core, a crack in the foundation of our understanding of reality that has persisted for over 100 years. Despite our best efforts, from brilliant experiments to breathtakingly creative interpretations, no consensus solution has emerged. The scientific community remains divided, with each proposed answer demanding a trade-off so significant it reshapes our entire picture of existence. This enduring impasse reveals something essential about the nature of discovery. It demonstrates that the most advanced frontiers of science do not simply separate into neat categories of solved and unsolved. Instead, they often blur the lines between disciplines, forcing physics to wrestle with questions that feel deeply philosophical. What is real? What is an observer? What does it mean for something to be a fact? These are no longer abstract musings. They are urgent, practical puzzles that emerge directly from our most precise mathematical descriptions of the world. This unresolved mystery is far from an academic exercise. Its echoes are felt in the most tangible technologies of our time. The entire enterprise of quantum computing is a direct confrontation with the measurement problem, a daily battle to protect fragile superpositions from the decoherence that seeks to collapse them. Our ability to push forward, to build more powerful quantum machines and more secure quantum networks, hinges on deepening our grasp of this very transition from possibility to actuality. Furthermore, the problem may be the crucial signpost pointing toward the next great revolution in physics. Our failure to cleanly reconcile the quantum and classical realms within our current theories strongly suggests that a deeper framework awaits discovery, one where the act of measurement is not an awkward postulate but a natural consequence. Solving this riddle could be the key that finally unites quantum mechanics with gravity, revealing a unified reality beneath the seemingly separate worlds of the very small and the very large. Ultimately, the story of the measurement problem is a powerful testament to the unfinished nature of scientific revolution. It reminds us that our understanding of the universe is not a completed monument, but a living, evolving narrative full of stunning insights and stubborn, beautiful mysteries. It invites us not as passive spectators, but as engaged thinkers to ponder these profound questions alongside the physicists and philosophers. The search for how possibility becomes fact is more than a technical pursuit. It is a fundamental human inquiry into the nature of the reality we all share, and in that ongoing search, in the willingness to sit with the discomfort of not knowing, lies the true spirit of discovery.